This week we'll be discussing processor design, and as announced earlier that this topic is not going to be included in the forthcoming test. All right. Processors, lies at the pivot of any large digital system. And it's really a challenging task how to go ahead for, if we want to design a processor as a designer, as a computer engineer, then what are the steps you need to follow? So today's processor comprises billions of transistors, and therefore, as you see that coming up with a very large design, it's not so easy task. So what we are going to do is to show you some generic approach, some simple approach, which is based on the RISC architecture, and that will lead to step-by-step design of the different components, and then combining everything together so as to which will implement the set of instructions. Which will implement the instruction sets, and thereby realize the functionality of a processor. We have covered all these topics like CPU performance equation, Amdahl's law, and so on. MIPS assembly language instructions, then number systems, integer floating point arithmetic, algorithms and hardware. So this is now the next step is the most important one, that moving into the processor design, that how we are going to interconnect these ideas. So now we understand what are the CPU parameters. What parameters would improve, would impact the CPU performance. We understand the nature of instruction set. We have understanding of the instruction set architecture. We already know that what are the constituents of a typical assembly language, for example, MIPS. And we have some idea about realizing computer arithmetic like addition, multiplication, and so on, including both in the integer domain as well as in the floating point domain. So as we see that when you attempt to build a very large system, that's always difficult unless you have a very systematic design approach. As I mentioned, that CPU is the centerpiece of any digital system, so it's the steering wheel of any computer system, right? And considering the hardware realization, if you want to achieve or implement its hardware realization, there are many steps. We understand that how the instructions are executed in a machine. We are familiar with the instruction cycle. There are several steps which you need to perform, like instruction fetch, decode, execute, memory access, and write back, and so on. So keeping that in mind, we should be able to execute each instruction in a certain sequence. That means my hardware should be such that it is able to support this kind of sequencing of execution or instructions. And in the process, we need to handle these arithmetic steps, data transfer moves, branch statements, and so on. And not only that, you need to coordinate among all modules. And therefore, we need an overall control of the computing of the processes. And if you want to achieve that, if you are capable of doing that, then it will be possible for us to come up with a design of a CPU. So let us look into some instances from nature. So what it is on the left, you see a picture. What it could be. As you can see, there are multiple processors or small. There is small, this spherical sort of stuff. So incidentally, this is nothing but the compound eye of a mosquito. And if you look into this tiny creature, well, it is a fantastic. It has fantastic capabilities, and it is a very complex system. It is a very complex camera system. It can see almost 360 degrees around it herself. It is a very accurate flight control, although it is a very small CPU, but it has very powerful remote sensing and olfactory capabilities. They can smell you from a long distance. They have nice navigation capability, decision making, and autonomous. And above all, it is very miniaturized and low energy requirement. And when you target designing a CPU, we need to keep in mind all these parameters. That it should be autonomous, it should be low power consuming, and it should be able to manage different kind of complex sequencing. Eventually, this is designed by nature, it is engineered by nature, and therefore it is error-free, and eventually it is optimal design. So how about when you are confronted with the task of a CPU design? So what are the challenges? First of all, let us understand the challenges. What are the goals? What are my inputs and outputs? Then we will be able to focus on the synthesis processing. So what are the major issues in processor design? Please tell me one or two parameters. Start from the economic point of view. What are the major issues? When you go to the market to buy a computer, first of all, what do you look into?
The processor power.
Processor power, also how much money you have to spend, right?
Cost, compatibility.
Yes. So cost, speed, capability. I mean, the processor power, as you said, yield. Yield is important because yield is a matter of concern to the manufacturer. It is the fraction of the good chips that is produced. So therefore, if yield is low, then the cost would increase. Then portability, that your processor should be able to you should be able to use that processor for multiple applications. Testing and fault tolerance is very important because the robustness of operation is of utmost importance, particularly in mission critical systems. So for example, in an aircraft, whatever chips or processor you're going to use, they must have very high fault tolerance or error tolerance. And they must be easily testable, right? We are talking about thousands and billions of transistors, so who knows that all of them are functioning correctly? So you need some kind of test procedure from time to time. At the same time, some fault tolerance or error tolerance kind of thing. That means if something wrong happens, the processor should still be able to perform its desired functionality and should give you indication that, well, there's some defect have already arisen. Now, also nowadays, the security is one of the main concern because as we see that the processors are often, unless you take appropriate steps, the processor or the hardware, it becomes vulnerable to external attacks. And so therefore, nowadays the hardware designs they must take care of the security issues. Another very important issue is the IP protection or intellectual property protection. It means that when a company designs a processor, say for example Intel, after so many years of research they have come up with some design. Now, they may not manufacture the design. So for manufacturing, there are other third parties. So for example, in Taiwan, you have TSMCs like Taiwan Semiconductor Manufacturing Corporation and so on. So what the designer do that, so you pass the design to them and they actually do the semiconductor fabrication. And in this process, what might happen that your design IP or whatever you have designed so far, the entire design information can be stolen by some other third party, so that your competing company would get the same design without doing much research. And so therefore, IP protection is very important. You need to what do I say? You need to encrypt your design in such a way so that the netlist behind you, that means the actual circuit description, cannot be so easily extracted by a third party. So those issues need to be considered when your objective is to come up with a processor design, and of course market demand. What are my inputs? And then what are the goals? One of the goals, as you know, that I want to make my cost low. it should be, its capability should be high, its speed should be high, and so on. What are the constraints? There are many constraints. As you can see, that the cost is one of the constraints. Power is constrained, and then heat dissipation or energy dissipation is constrained, because otherwise the chip might burn out and may degrade, its functionality may be degraded. And then silicon area, time to market. There are many parameters like that which impose different constraints on the designer and the manufacturer. And moreover, and above all that, how do I automate the entire design process? Because everything should be done with the help of some automated design automation tools or computer-aided design tools. Because without tools, you won't be able to, it is not possible to design such a very large system. So these are our challenges, and what are my inputs? Well, we start with instruction set architecture, that is the middle line. And given the instruction set, once the instruction set architecture is defined, then we can go down, we can go towards the bottom side to design the hardware which is required to support the instruction set. And on the top, you would keep on designing the required software to envelop the machine with more and more like operating systems and other application softwares and so on. So what are my inputs? The inputs are the set of instruction set. And when I say instruction set, it means that the list of instructions, what are their formats, what kind of addressing modes are embedded in it. That means not only the instruction set, but also the semantics associated with the instruction set. Both the syntax and the semantics associated with the instruction set. That I need to understand, because otherwise I won't be able to design my hardware, which is necessary to support those. What sort of what sort of registers you have, how many of them, what are the register size and so on, word length, what would be my memory addressing capability, all this information you need. So these are my inputs. And we have some basic components, because we are not going to design everything from the scratch. So we are going to use some components which have already been designed. For example, ALU blocks, arithmetic logic units, which comprise the adders, multipliers, and those kind of stuffs. And we need some basic logic blocks like multiplexer and storage element flip-flops. So these are my inputs: register files, program counter we need to keep track of the execution of different sequences one after another, and of course memory. And we need some clock system to synchronize everything. We are talking about clock cycle time and so on. So we need a global clock for synchronizing all operations. So these are all my inputs. And what is my output? The output design is I want to come up with a hardware system such that which is capable of executing the given set of instructions under program control. Okay. So you have some understanding of the challenges, what are my inputs, what are the outputs, and what are the constraints and so on. So given that, let us know what are the other issues. As you see, that CPU performance is an important issue, which is determined by the instruction count, average number of clock cycle per instructions, and clock cycle time. And they depend on this instruction set architecture and compiler. CPI and clock cycle time, we already discussed that. This is determined by the CPU hardware and so on. So we'll discuss two generic, very simple generic implementation. Don't be afraid with hardware circuits and hardware systems. We'll start from the scratch and just show the step-by-step procedure in order to implement a very simple machine. So first of all, we'll consider a simplified version of a CPU, and this is called single cycle execution, meaning that in our instruction set we have many instructions, but my clock cycle time is such that every instruction can be executed within a single clock cycle. That is my basic assumption for this version. And this is easy to understand and easy to design. And then in the later part of the course, we will talk about the pipelined machine, and which is more realistic. And then this is essentially some kind of multi-cycle representation. So we'll talk about that later on. Right now, we'll discuss single cycle execution, meaning that every instruction will be executed within a single clock cycle. And typically, what sort of instructions we have in an assembly language? We need this data transfer kind of thing, like memory reference. Now, MIPS, as you know, is a load store kind of architecture. So therefore, when you access memory, there are separate instructions like load word, store word, and so on. And we need to do some arithmetic and logical operation. So we will consider some basic operation like add, subtraction, logical and, or, and this is shift less than, SLT, and some control instructions like branch, equal, and jumping. So this is a subset of instruction which we will consider for our implementation. So that this typically covers the three different types of instructions like memory reference, arithmetic and logical, and control instructions. And the design we are going to show right now that will take care of this small subset. Okay, so as to give an overall idea that how the processors can be designed. So first of all, we'll focus on only arithmetic and logical set. That how do I implement addition, subtraction, and or an SLT. Now, as we have already seen that when you studied arithmetic circuits, we already know that how to design a 32-bit adder, how to design a 32-bit subtractor, and operation between two registers. That's very simple because you need to all you need is an array of AND gates, and similarly, or SLT we will discuss now. So let us start with a very simple example. So we'll start from just a single bit CPU, and then we'll show that how you can design a 32-bit CPU which is capable of executing these 5 basic instructions. Okay, and then we will move on to this load, store, and branch, equal, and jump. So execution time, this is our familiar equation. We have seen this equation many times. We have clock cycle times and clock cycle power instruction. So if I do it everything in a single cycle, what would be the value of CPI?
One.
Sorry?
1.
Yes. A single cycle processor, clock cycle, power instruction, CPI would be 1, because in one clock cycle, within the clock cycle time, we are going to execute each and every instruction. So its advantage is CPI is 1, and the design may be easier, but on the other hand, the disadvantage is the long cycle time, because all the instructions will be penalized by by the slowest one. So anyway, so we'll first consider single cycle processor. So we start with designing a very simple ALU first. We'll start with 1-bit ALU, which you have already seen many times, and then we'll build 32-bit ALU. And this you also have seen this so far when you talked about this arithmetic design. But still, we will start from the scratch and show the steps. Okay, so let us build an ALU to support and or addition, subtraction for integers. So we just built 1-bit ALU and use 32 of them in a series to construct a ripple carry sort of stuff. So this is our basic unit for 1 bit. We have 2 inputs A and B. This is 1-bit input, and we have an operation to specify here, maybe addition, subtraction, and the result I'm expecting here. And then once this 1-bit ALU is formed, what I'm going to do is to just take the copies of them and connecting them in series to implement the 32-bit processor. Well, so let's first look at 1-bit ALU for addition. We already know about it, that this is the majority function and the parity function. This can perform the sum and our sum operation. So what I'm going to do is if I do a 32-bit ALU, let us look into this block. This is a 1-bit ALU for performing and or an addition operation. So this is one-bit input A, and so you have 2 inputs A and B, and I use a single AND gate here, a single OR gate here, and this is the full adder block here. And I use a multiplexer here, and this is the operation. It means that depend which operation you want, and that gives you a control line here. So if you want an AND operation, I will let this input to pass here. If I want OR operation, I will let this signal to pass here. So, and if I want to perform addition, I will let this output to pass. So this is a 1-bit ALU for performing AND or addition operation. Okay, so 32-bit is easy because we connect them in series, just like ripple carry adder. And so we have 32 bits running from A0, B0 to A31, B31, and they are connected in series. And this operation, the selection line, which selects among this the logical and arithmetic operation, that should feed all the units here. So this is the 32-bit ALU, which is capable of performing logical AND operation between two 32-bit operand, OR operation, and addition operation. All right. Very simple. Now, subtraction, as you know that 2's complement subtraction, we don't have to do anything. All you need to just invert the B 1 bit and then add and do this carry input 1. So we do this modification here. So we use a multiplexer here that takes care of this inversion. And so this will perform, this is 1-bit ALU for performing AND or addition and subtraction. Okay, so this you already and have seen many times. Now we are going to add this instruction. How to support set on less than instruction, SLT, RD, RS, RT. Now what does it mean? If the content of this register is less than this, then you set RD to 1, else RD to 0. So in order to do that, what I need to do, I need to subtract the content of RS and RT. And if this is negative, it means that the condition is satisfied, right? And then we also want to support the test for equality, this branch equal T1, T2 level, and that also need a subtraction operation. Okay, so please tell me now that if I want to implement this set less than instruction using 32-bit operands, then what I'm going to do? I already have a processor which is capable of executing addition and subtraction. Then what additional data paths we need so as to implement this? I need to do subtract, and then what? Okay, so this is the basic unit, and we also add some hardware here for detecting overflow and so on. And this is the unit for inversion, so that you can do subtract operation. And now I also add an extra line here and increase the size of the multiplexer. Well, in order to do SLT, what I need to do then? SLT means this. If the content of RS is less than RT, then I'm going to set this register, this destination register to 1, else RD to 0. Now, what is meant by setting RD to 1? That means when the condition is true, that means if this is negative, or this is less than 0, then what would be the content of RD? RD is setting to 1, right? It means the least significant bit of this register should be set to 1. All other bits should be set to 0. And if this condition is not satisfied, then all bits should be set to 0. That is the meaning of the SLT, right? Set less than, what do you set? The least significant bit of the register is set to 1 when this condition is satisfied. Okay. So what I need to do then in the hardware, given the previous 32-bit logic,
Sir, shift RS minus RT by 31 positions to the right. So if it is negative, then the 32th bit will be 1. So that
Right.
will be set to the first position.
Right.
Otherwise, it will be 0. So all 0. So RD will be 0.
Okay, that's it. And so keeping this in view, my hardware would be very simple. Okay, so I have this 32-bit ALU, which is connected in series like RCA. And this is A0, B0, this is A1, A31, B31. That means this is the 32nd bit. And I know that if I do subtraction, so then this output, the last output, this last sum output, that would be that. And if this is less than 0, then this is the sign bit, right? So that would be 1. So I tap that bit, I tap that. So I take, so in my hardware, I just use this bit and go to the first here, go to the first one, the 0th one, because I need to set the least significant bit here, right? So I'm going to pass this bit here using this input line. See, there is an extra input line here in this module, which is marked as less. Okay, so this one bit which is observed here after subtraction operation, if it is negative, then this bit will assume 1, and that 1 is you apply here in this input and pass it to the output. And since the rest of the bits are set to 0, and therefore the third input of all these inputs, all these modules are set to 0. Look at this diagram carefully. So this is the block. I have 3 inputs, A, B, and there is a less input here. And so what I'm going to do that A, B, they receive the actual bits from this RS and RT. And the third input, they are all set to 0, excepting the first one, which takes its value from the sign bit of the last, the sum bit of the last adder. Okay. So this and whenever you get these values here, those values, this vector will be used to load the destination register RD. So just by simple hardware modification, so you have an adder and a subtractor, and then what you're going to do is just do some kind of a little bit feedback here to set this bit, this significant bit. Otherwise, if it is 0, I mean, if after subtraction, if it is not smaller, then the sum bit will be this will be a positive number, so the sum bit will be 0 anyway. So that 0 will set this least significant bit, and all other bits are set to 0 by the direct input lines. So this simple hardware implements this set less than RD and set less than instruction. So now, suppose I want to implement this branch EQ T1, T2 level. So how would I do that? Again, I need to do subtraction. And if this is 0, so that means that all the sum bits will be 0. Okay, so very simple. Just tap all the sum bits, use an OR gate here. So if all of them are 0, then that means so output of the OR gate will be 0, and this out, and I use an inverter here so that this 0 line would be set to 1. Okay. And so therefore, this simple ALU can perform addition up to 32-bit operands, a subtraction, then logical AND, logical OR, SLT, and branch EQ. We have a small ALU that can perform these basic sets of instruction. The output 0 becomes 1 when the branch is taken, because all the bits will be 0. The difference will be 0. And so the PC, of course, the PC need to be updated because you need to jump to this level value. So the content of the PC need to be updated accordingly, so that instead of going to the next instruction in sequence, it moves to the instruction which is pointed by this level value. The PC need to be updated accordingly. That we'll see how it can be done later. So here, what I want to point out, I want to show you that this simple ALU is able to perform 32-bit addition, subtraction, 32-bit logical and logical OR, SLT operation, and branch EQ. All right. So now, So this is easy to understand. And once you look into this diagram, all the operations becomes sort of trivial. Well, so this ALU implements the arithmetic instructions, logical instructions, and SLT and branch. Symbolized as we use a small symbol like this. This is the control lines. That means the lines which are controlling the outputs or the inputs of the multiplexer. And why we need this 3 bits here? Because the multiplexer you saw that has that multiplexer. This is a 4 by 1 multiplexer. So we need 2 bits for the operation line and 1 bit for this bit invert line. And that's why you need to see the control lines. There are 3 bits, 2 bits for here and 1 bit for the invert line. Well, okay, so we are done with this simple set of instructions, and this is symbolized as this module. Well, we recap the execution cycle that we have: instruction fetch, then decode, and register read. And then you execute the instruction, and then memory access, result store, and next instruction, and keep on doing this. So these are, in MIPS, we have this basic 5 stages: instruction fetch, instruction decode and register read, execute, memory access, write back. So remember these 5 stages. And when you are going to do our CPU design, we need hardware implementation of all these steps. And let us see that how we can do that. Instruction execution, well, we need a PC, of course, so that which provides you the next address of the next instruction to be fetched. And for each, we have a register file that comprises these 32 registers and so on. And we need some register numbers or register ID in order to designate a particular register. And depending on the instruction class, we may invoke the arithmetic logic unit to compute arithmetic result or memory address and also branch target address. And for all these operations, we need the arithmetic logic unit, either for performing addition or subtraction or arithmetic operation, computation of the memory address for load store that also needs the addition process, and also branch target address. This also needs an addition process. And then access data for load and store. And we need a mechanism for incrementing the PC regularly. So the current value of the PC should be incremented by PC plus 4 unless there is a branch or jump instruction. So basically, so let us look into this diagram, and this in the block diagram, this shows you an overview that what sort of stuff we need in a CPU. Okay, so let's look here. This is a program counter. This is a 32-bit program counter that we need. And as you see here, so this is a small ALU which can add this constant value 4 with the content of the PC. So therefore, this output of this ALU would be PC plus 4 whenever needed, because as soon as the instruction is executed, I need to update this PC so that it can bring the next instruction. So therefore, this is the mechanism which performs this PC plus 4 operation. Now, sometimes when you have branch and jump, those kinds of instruction, then it's not PC plus 4, it is something else, because that information is available from the level of the branch instruction. And the level of the branch instruction can be extracted from the instruction memory. That means this instruction memory holds all the instructions, and you are looking into one instruction at a time. So in the instruction, there are some fields which gives you the address information of the label when you have a branch instruction. That information has to be extracted, and you need and that's why it should be added to PC plus 4 to get the target address of the jump or branch. That's why you need some kind of hardware here. So we'll talk about this more in later on in more detail. Also, you need a register file here. These 32 registers. So this is called a register file. And you need some inputs and outputs. If you want to identify the register, so you put the ID information here, and then the content of the register is read out through these outputs and is supplied to the ALU. And if you want to write something to the register, that is taken care of by this data path. Okay, and this is the ALU which performs the major arithmetic operation and the computation of the target address and so on, the load and store addresses. And so for simplicity, we assume that our memory has two components here. One is instruction memory and data memory. So let us assume for simplicity at this moment that we have separate instruction and data memory blocks. So as you can see that we need a couple of modules like that. We need an instruction memory block, we need a data memory block, we need a register file, we need a couple of ALUs to perform certain operations, we need a program counter and some data paths. So we'll keep on expanding this diagram and we'll add more and more details to it, so that you will see that how different instructions can be executed. So this is a kind of overview, is a very abstract view of the overall CPU. All right. Okay. So as I mentioned, that this CPU takes care of the computation of the target address whenever you have a branch or jump instruction. So we'll come back to that. Two types of functional units so we need. Elements that operate on data values, that means the combinational blocks, and the elements that contain the state or stores the value, that means the sequential blocks. And as you see that here there is a combination of data paths. One data path is going this way, another data path is going this way, and so there are two inputs and one output. We cannot connect these wires directly, right? Similarly here we have one input here, another input coming from here, and they are going to the same destination. So we need to insert some multiplexers here. Similarly here, okay? So that we will do later on. So we need some multiplexer to stitch the data paths. We cannot just join wires together. So we'll use multiplexer whenever needed. And as we will see the later designs, we'll show that. Okay, so this will be replaced by multiplexer later on, because you have multiple inputs and a single output. Okay. And once you insert this multiplexer, the processor would look like something like that. Okay. So don't worry about this, the complexities of the design and these data paths. We'll gradually see that how these data paths have been defined. So just to have some idea that, okay, let us just look into this, the modules block by block. You need a PC here. This is the stuff which takes care of PC plus 4. This is the stuff which takes care of the computation of the branch or jump address. And this is we need a mux here. Either it could be PC plus 4 or it could be something else, the target address. And we need a mux here to, and then you load the PC with the appropriate value. You need a register file here. You need a mechanism to read the register and feed the data to the ALU. And in the ALU, we have a zero line, as you've seen, because we have already seen that we have a zero line that we have just designed. And that zero can be used here using an AND gate to, if it is a branch, then, then some information would be needed here to load this mux. And we have a data memory here where you can access for load and store kind of thing. Well, so let us not worry about this data paths right now. This is just an overview of the whole thing, and we'll keep on developing this step by step. Okay. And our ultimate objective is to implement all these 5 stages, like instruction fetch, decode and register read, execute, memory, and write back. So what are the combinational elements? These are the elements which you need. We need an adder block that we have already seen. We need a multiplexer. These are the basic modules we'll be using in our design. And this is the basic arithmetic logic unit, 32-bit. And these are the function selection line. We can do addition, subtraction, logical AND, or SLT and branch. This is a simple ALU, just to perform A plus B and so on. We need multiplexers, couple of AND gates and OR gates. And as sequential elements, we need flip-flops. In fact, the registers are just a series connection of flip-flops that stores data in the circuit. And we need a clock signal that determines the clock cycle time. And so all the stores, the state elements of flip-flop should be synchronized with an external clock with a given frequency. And we typically assume that the output changes when the clock edge goes from 0 to 1. This is called edge triggered. And this is necessary to avoid certain kind of electrical oscillations and so. So basically, if I have some data is changing here, and this is the output, and when the clock goes high, then only the data is captured. So the data is captured and made available to the output only when there is a transition in the clock from 0 to 1. For rest of the time, the data you are on hold. And again, you make a transition from 0 to 1. So that means, in other words, if forgetting about this timing diagram, what happens that this output becomes transparent to the input only when the clock experiences this edge trigger from 0 to 1. All other time, this output will hold the previous value. You follow me? Well, and we also in the register file for each flip-flop, we also use an external control which is called the write, and this is needed so that you don't accidentally change the state of this flip-flop unless you really want to. So in order to write, what you need to do that you need to feed the data here. You need to feed the clock. At the same time, this write signal should be enabled. Then only this flip-flop state will change. So this is done for extra safety, so that this output does not accidentally change with any other kind of sort of stray signal. So it's called the register with the write control. The update is done only when the clock edge is controlled and the control input is 1, and the clock experiences a transition from 0 to 1. So therefore, you have this D signal and the Q signal. This is the clock signal. You need two conditions to be satisfied. The clock should go from 0 to 1. At the same time, the write signal, this signal should be enabled. That means this should be high. Only in that case, the data will be captured and will be made transparent to the output. If the write signal is disabled, then it will hold the previous value. So so this is nothing but this complication is necessary in order to make this write operation a little bit safer. Well, so these are the things we need, and we are going to now add more and more instructions like load and store, and we'll see that how this can be accomplished. First of all, let me talk about the register files. In a register, so there are 32 registers. For example, in MIPS, there are 32 registers, and this is in block diagram. This is shown as a register file, like this. What happens that so there are 32 registers. So there is a mux here, and since there are 32 registers, this mux has 32 inputs. Now each input is 32-bit wide. Okay, so these are buses, and this is the line which selects the particular register. That means if you want to read register 1, then the corresponding register ID should appear here, and then that particular register ID is accessed here. That means you can access the content of that particular register here. So how many bits are there in this line? In this read register, this line?
5.
Yes, 5 lines are there. And each input of this multiplexer, there are 32 bits, 32 lines here, and each line is 32-bit wide. Mind that. And in the register file, we have a mechanism of register reading 2 registers, because see, in MIPS operation, we often need to read 2 registers. So for example, add T1, T2, right? Subtract T1, T2. So you need to read 2 registers. And so therefore, in your register file, you have this kind of mechanism which is hidden. I mean, internally, this kind of mechanism is there. So for example, this one, add RD, RS, and RT. So you need to add RS as well as RT. Information about RS is coming through this register ID. Similarly, for information of register RT is arriving through this bus. So these are 5-bit wide. And this multiplexer allows you to access the particular register you want to read, and that data would be made available here. And this whole thing is designated by this shortcut. I mean this symbol, this compact symbol. So that means in this box, see there is a write enable line we have just discussed. In order to read the register, write to the register, you have to make this this line should be made 1. Okay, and this is the read register number 1. So this is the 5-bit ID for register 1. This is the 5-bit ID for the register number 2. And if you want to write to the register, then there are data lines here, and this is the write data line. Write data line. This is 32-bit because 32-bit data will arrive here, and this is write register is an access, is some kind of enabling line, and the read data is available here. These lines are 32-bit wide. These are all buses. So the whole thing is, in shortcut, it is represented by this box, the register file. And inside there are 32 times, I mean there are 32 registers, each 32-bit wide, which are frequently, and they are numbered from 0 to 31, as you know, in MIPS. Okay, so that's all about reading. How about writing? When you want to write to the register file, then, okay, first of all, use the clock to determine when to write, and the write line is enabled to make it more safe. And you need to access to the register. The particular register, there are 32 registers, and you want to access the one to which you want to write. So therefore, the destination register information is arriving here. And now, as before, this is a 5-bit input line, and there is a decoder here which decodes this line and access and made this particular line 1 in. Okay, and this decoder actually selects this from the register files, the destination register, and then you make this this write line enabled. This AND gets they take care of that, and the data to be written is supplied here to the particular register. So that's inside this, in the register file, which you don't see. Everything is represented using this box. So we have this read mechanism and the write mechanism. We have this you have a logic design with multiplexer here for reading, and with decoder for writing, and this entire thing is represented by this box. We'll be using this box later on to see in our block diagram, in the overall block diagram of the CPU. So that's what is inside in the register file here. Any question here regarding register read and write? How to access register for read and write? Just remember that how many bits are, when you see such a diagram, just check on yourself that how many bits are there, and then you will see what is happening. Okay. So for example, here, after you perform the addition operation, then the result should be stored in this register RD. So that register RD information about this ID of RD is register number is being provided here using this 5-bit binary string. This decoder now selects the particular register from the file, and allows this the data line to access that particular register. And this is the write enable line, so that the write operation can be performed. And of course, you need the clock signal to execute the write operation, so as to synchronize it with the remaining portion of the CPU. So that's all in the register read file and write file, and using this basically. So now in this in this slide, you see that these are the blocks which you are going to use. Okay, for simplicity, we'll use, this is my memory block. You may assume that my cache, main memory, everything is here. We are not going to discuss the detail of that memory hierarchy here. Assume that this is memory which is accessible when an address is passed here. So we have instruction memory, we have data memory, and we have the program counter, which is represented by this symbol. We have an adder, small adder for performing PC+4 and so on. We have a register file. Here you can see this is the read register. This is 5-bit ID, you know. Write register also 5-bit line. These are data lines containing the, reading the content of the register. So these are 32-bit lines. This is the register write enable line. This is single bit line. This is the write data. This is 32-bit line. Okay, so this is for reading the register. This is for writing to the register. This is writing enable line. These are register access lines. Okay, so this block we'll be going to use. These are my basic blocks which you are going to use. And this is my ALU, which you have just designed with 5 operations like addition, subtraction, and or SLT branch. And we also need this module. You often know that, see, we have this, we need to extend the 16-bit sign, 16-bit address to 32 bits. For example, when you have a branch instruction, or if you have an add immediate instruction, like you have an offset value of 16-bit, and then you need to extend to 32 bits for addition operation and for further operation. So we need a hardware that takes the 16-bit as inputs and provides the 32-bit sign extended. That means the most significant 16 bits is filled out with the corresponding sign bit. So that's nothing but you need a small hardware, a piece of hardware here, which performs the copying of that bits to the most significant 16-bit positions. This is called sign extension. So these are my basic hardware blocks or units, which we are going to use for implementing the overall CPU, and that we will do in the next 2 classes. So that we don't have to worry about what is inside the register file, what is inside the ALU, and so on. Does it make sense? You follow me? So these are these are the basic blocks which we are going to use for designing our CPU, and that will show that how you can do that in the next few classes. All right. Well, let me stop here today. We are done.